Buenos dias, amigos tensores. Good morning, tensor friends. Uh, Last couple of days, we've been working on position vectors as derivatives of arc length. And I know you're thinking, why are you boring us with this crap? The reason is so we could get to this. We want to derive curvature using tensor calculus so that we come up with an invariant equation that works in any coordinate of the system. Okay? So let's get cracking. Now here's what I've been boring you with is the details of deriving a position vector with respect to an arc length, and it come up to be the unit tangent vector. We called it S hat. Okay, and now what we want to think about is okay, we have been taking this derivative as a function of arc length. Well, what if we want to take it with a different parametric? And I'm going to choose t. Okay, so we can, using the chain rule, we can write dr dt as dr ds and ds dt. Well, we just said what this was. We went through this in agonizing detail. This is just s hat, right? So that leaves us with ds dt. Okay, now what can we do with this? Well, one of the things that we can do is take this here to the other side, and now this is a vector. We're taking a derivative of a vector as a vector. Here's the vector, and here's its component. So this is a scalar. So we can take this to the other side. So here is dr ds, here is dr dt, and we just flip this over, and we get dt ds. We can do that because it's a scalar, right? Now we want to take the second derivative of this expression with respect to that parameter t, okay? Now I colored this in blue because we're going to break it out. So here's my operator acting on the left-hand side. Here's my operator acting on the right-hand side, okay? Now let's break out the blue stuff, okay? Now, we can break this operator up into, also using the chain rule, as d by ds of ds dt. So you would agree that this is the same as that, okay? And since the order of differentiation isn't important, I can just move this inside as I just did. Now we have d by ds of this, which is already differentiated by s. So we get the second derivative of r with respect to s, and once again our ds dt. Okay? Now we've got this piece, so we're going to put that right back in here, and we got this equation. Okay, well, what are we going to do with this? Well, because this gets real messy, I'm going to change anything differentiated with respect to t, that one, and this one, to a r prime. Now, traditionally, this is done with an r dot, but in Google Docs, putting that dot over that r is hard, and putting a double dot over is impossible. So I gave up. Let's just go with the prime. It works just as well. As long as we all agree what it means, it's not going to be a problem. Okay, so we've got our second derivative of the position vector with respect to arc length. ds dt becomes s prime. Here's our operator. dr dt becomes r prime. And now look, if I flip this over, it goes in the denominator and it just becomes s prime. Oh, so that's the reason I did this, because this equation becomes very messy. All right, so we use the quotient here, the quotient rule here, or you can put s prime up here with a -1. Use the product rule, you get the same answer. All right, so it's the numerator times the derivative of the, let me start over. It's the denominator times the derivative of the numerator. So it's s prime r double prime minus the numerator times the derivative of the denominator, r prime s double prime, divided by the denominator squared. So this is the quotient rule, okay? Now, once again, this is a scalar, right? So we can just take this to the other side, which would make this s primes cubed. And here is our equation. So this is the generalized form of the curvature equation. works in any coordinate the system. Now, this is a tensor equation. This is not what you saw in calculus, and we'll get to that in a minute. All right. So to make sure this works and we know how to use it, let's do something really simple like the curvature of a circle, because we all know what that is. Okay. So here's an example. So we have a circle with a constant radius r. So our derivatives will be with respect to theta. So that's our parameter. T in this case is theta, right? So here's the equation of a circle. So we differentiate that with respect to theta, we get this. Differentiate it again with respect to theta, and we get this. So now we have the two pieces that we need. Now we need our metric, okay? So here's the metric equation, the infinitesimal arc length invariant equation. It's a mouthful. All right, and here it is in polar. The coordinates, we did this in the last video, remember? Now, we want to take the derivative, first take the square root. We want to take the derivative of that with respect to theta, okay? And that just becomes d theta equals the square root of r squared. This is what we did in the last video. So s prime, this would be s, in our case, s prime is just r, and s double prime is 0 because that's a constant. We're not changing r. R is a constant. Okay? So here's our generalized equation. And we put that stuff in we just found. So here's s prime. R double prime is this. S double prime here is 0, so that wipes that out. That's lucky. And here is S prime cubed. It's just R cubed, okay? So we distribute the R. We get this. Once we do, the R cubed takes that out, leaves one R in the denominator. We're left with this expression. Now, the curvature is defined as the magnitude of this vector. Now, this is a vector, right? You see here, it's got basis to vector. So this is a vector. So the curvature is defined as the magnitude of that vector. Well, how do we find the magnitude of any vector? Well, we multiply it by itself and take the square root. So that's what we're going to do here. Now, remember, ex dot ex is 1, ex dot ey is 0. Ey dot ey is 1, ey dot ex is 0. So we only get two terms. We get cosine squared theta plus sine squared theta over r squared. And we know what that is. That's 1 over r squared. So the square root of that is 1 over r. Okay? So this is the curvature of a circle. Curvature of a circle. And the radius of curvature is defined as r equals 1 over k. So it's just r. So these are two values that is very common in doing this. So this is truly the beginning of tensor of Riemannian geometry, is understanding how curvature works and how this relates to surfaces. Okay. Now, I have done this in Tensor, the format, and I'm debating with myself whether to go into that next because it is extremely complicated. And I did a playlist on it. I may dig through that playlist and try to come out with some things that are not so nasty. There's a lot of nasty equations in there. It took me a month to do that, and no one watched it. So it was kind of disappointing. Okay. Now, this equation, if you set r equals to a position vector in Cartesian, the coordinates, the metric in Cartesian, the coordinates, you differentiate all this with respect to x, and you plug it into this, you're going to get this equation, which is what you saw in calculus. I'm going to think calculus 2, is that right? I'm thinking that. Where they defined the curvature as this. But this only works in Cartesian coordinates. This is not a tensorial equation. This is the invariant format for curvature. Okay, so that ends that part, and we're going to keep going. All right, thanks for watching.